So now let's have a look at this question. This question was sent by one of the students, right? So now the question, it involves the compressibility factor. So the question and the statement reads as follows. They say to us, propane in a steel bottle of volume 0.1 cubic meters has a quality of 10% at a temperature of 15 degrees Celsius. Use the generalized compressibility chart to estimate the total propane mass and to find the pressure. So now at this point in time, let us just write the given information. So we are actually provided with the volume. So our volume of propane is going to be 0.1 cubic meters, right? Then we are also provided with the quality at this point in time. It's going to be 0.1, which is 10%, which is 10 divided by 100. And then our temperature of this gas, of propane, is going to be 15 degrees Celsius. And then they want us to use the compressibility chart to estimate the total propane mass and to find the pressure. So basically, we are looking for the mass of propane, and we are also looking for the pressure of propane. So let me ask you this. How are we going to determine the mass? Now, at this point in time, there are many formulae that you can think of, right? But for a fact that this question, it involves the compressibility chart. The equation that you're going to use to calculate mass, it is the compressibility equation. The equation, it is denoted by, this is the given information. The equation, it is actually denoted by Z is equals to pressure multiplied by the specific volume divide by R. I'm going to write the specific R over here, just represent it with dash because it is divided by molar mass of the propane, right? It's divided by the molar mass or molecular weight of propane. It's not that the R that we know, the constant ideal one, this one. It is actually the one that is divided by molar mass. This one, it's given by the constant divided by the molecular weight, okay? And then multiply by the temperature. So this equation, it doesn't have mass, which is what we are looking for, but we can manipulate this equation to have mass. Do not forget that the specific volume, it is actually given by volume divided by the mass. So meaning we can make the specific volume subject of the formula at this point in time. So making the specific volume subject of the formula, we're gonna have our specific volume being equals to Z multiplied by RT divided by pressure, right? So this is how our equation it is actually going to look like. But remember the specific volume, it is denoted by this side we have volume divided by mass, which is equals to Z R bar multiplied by T divided by pressure. So to make the mass subject of the formula, I'm going to take the reciprocal on this side and multiply by that. So that means my mass will actually be equals to P, will be equals to PV over ZRT. So this, it is the derived equation that we are actually going to use to calculate the mass of propane. But the question is, do we have the pressure? We do not have the pressure. That's what we need to calculate first, right? Do we have the volume? Yes, we do have the volume, which is 0.1. Do we have the Z? So meaning we need to determine Z, we need to determine the pressure. And then do we have R? We can determine that using the molar mass, molecular weight for propane and the constant R. And then we have the temperature. So our struggle right now, it is the pressure and the Z. So how are we actually going to determine the because we cannot determine Z without knowing the T reduced and P reduced, right? So what I'm going to do here is firstly going to determine the pressure. So how am I going to do that? Now, this is simple. To calculate, we're going to firstly determine Z and then we determine the pressure. So to determine the value of Z, okay, we're going to use the table. So we know that T reduced is given by the temperature divided by the critical temperature, right? So we won't be able to determine P reduced, right, which is P divided by T divided by P critical. We won't be able to use this equation to determine the P reduced. Why? Because we do not have the pressure, we don't have the P critical. And then we can actually use T reduced to determine, we can determine T reduced by using temperature and T critical. So the P and T critical, they can be determined or obtained from the table, right? So what I'm gonna do here is I'm gonna take you to the table for propane. I'm gonna take you to the table to get the critical values, okay? So now let's go through the table to get the critical values. So now our critical values at this point in time, hope the table is so right. So the critical constants, here we have the critical constants for all of these substances. So we are actually looking for propane, right? So we are looking for propane. So let's look for propane, P. Let's go for propane. So now here is our, not propene, be careful, there is propene, unsaturated and saturated hydrocarbon. So we are actually looking for propane. And then here are the criticals. And then on this side, we are having the molecular mass, we are having the temperature, we are having the pressure. So we don't want critical volume. We want critical, even the molecular mass, we're gonna need it. So we need these two guys, these three guys over here. So let me write them down. So the molecular weight is gonna be 44. Where is it? Okay, let me highlight here so that I don't get confused. I'm here. So that means it's gonna be 44.094. I can use kilograms per kilomoles, right? Or I can use grams per moles. It is still fine. It depends on what units I will be actually using. And then what's this side? Oh, sorry about that. Temperature in Kelvin, right? In Kelvin. So my temperature in Kelvin, we have 369.8 Kelvin. And then our pressure, which is 4.25. So the units for pressure at this point in time, we have megapascals. We have the megapascals, right? So this is our critical values. So what I'm gonna do is I'm taking these critical values onto our question to perform the calculations, right? Right. So now what I'm gonna do here is I'm gonna be able to determine the the reduced temperature using the temperature critical and the temperature provided. So to get the temperature critical, what I'm gonna do here is my temperature, remember, I'm gonna have to convert it into Kelvin. So I'm gonna say 273 plus 15 degrees. I'm gonna get 288 Kelvin. That will be my temperature. Okay. So meaning here I'm gonna have 288 Kelvin divided by critical. So my critical here, I have wrote it down, it's 369.8 Kelvin. And do not forget, where did we get this from, right? 369.3. 0.8. And then what I get on my calculator, oh, it's 69, not 96. To two decimal places, I get 0.78. Right. So this is my temperature reduced. Now, after getting the temperature reduced, how are we going to get the pressure reduced? Are we going to be able to get the pressure reduced? Let's see. So we're going to use, and then you see our quality here, it's 0.1, right? So what I'm going to do here is I'm going to use my temperature reduced to get my pressure reduced. So how am I going to use this? I'm going to use the compressibility chart, okay? So I'm going to my compressibility chart, and then my compressibility chart is going to be this side, right? So now here's my compressibility chart, okay? So I'm going to use this compressibility chart to actually determine the I'm having T reduced. Remember our T reduced, we got 0.78, and our quality, it is actually 0.1. So to get pressure reduced, what am I going to do? So now I know we haven't done much of the basics when it comes to this question, but I want you to pay attention, okay? So now what I'm going to do here is we have these lines over here. This thing doesn't point, so let me do this. We have these lines over here, right? We have these lines over here. Now these lines over here, they represent T reduced, okay? But when you have a look at these lines over here, they start at 5, they move to 2, to 1.5, 1.3, 1.2. You see, they are actually decreasing until we get to this one where we have 1. And then until whereby these isotherms, they no longer curve like these ones that we see over here. Here they are further decreasing. We have 0.95, we have 0.9, we have 0.85, we have 0.8, and we have 0.7. So the number that we see over here, which is 0.78, is gonna be within this range over here between 0.7 and 0.8, right? Because that will be our T reduced. So what are we going to do to get 0.78? Now, at this point in time, to get our T reduced, we actually going to approximate, by the way. So if from, let's see, and then this side is going to be PR reduced. So I'll try to make half of these two lines over here, because half of just determine the midpoint where I'm going to 0.8 plus 0.7, and then I divide by 2, I get 0.75. So the middle of this line, I think this one will help me to, the middle of this line, I have 0.75, right? And then now I'll try to take the midpoint of 0.75 and 0.8. So meaning the middle is going to be somewhere else here. So what I'm going to do here is I'm going to say 0.75 plus 0.8 divide by 2. I get 0. Oh, I made a mistake. 0.735 plus 0.8 divided by 2. I get this value over here. I get 0.78, or which is 775, which can be 78. So meaning it's going to be somewhere else over here. I'll assume it's here, right? It's on this line over here. So now, if it is on that line over there, so it is my T reduced, right? These lines, they are all my T reduced. So my T reduced over here, it's 0.78. And then when I go down with my line, straight line, it's not straight, but make sure that you use your ruler. I'm gonna have to read the pressure, which is PR. I'm gonna have to read the pressure at this side. So now what will be my PR at this side? Now my PR at this side, I'll try to use this scale once more again to figure it all out. What is the value over there? So I have 1, 2, 3, 4, 5. Okay. So what is half? What is the midpoint of 0.1 and 1? So I'm going to say 0.1 plus 1 divided by 2. I get 0.55. So midpoint, the middle point, I think I would assume that the middle is here. I think it's somewhere else over here. It will be my 0.55. And therefore, the midpoint of this and that, 0.1 divided by 2, I get 0.33. So 0.33, I will assume that it's somewhere else over here. Let me see. To my middle point. Oh, I think here I'm supposed to move like this. The middle point here is gonna be here. Right. So this value over here, let me see how can I do it simpler, because now you see it's difficult because you have to, assume this, not assume per se, but yeah. So meaning I will say this is a little bit half of it. So I will take it as 0.33. Should I take it as 0.33? Yeah. So I'll take my value over here to be 0.33. Okay. I'll take it like that. So meaning our PR, however you see it, it's fine. Our P reduced, it's gonna be 0.33. Okay, I'm taking it like this. Okay, so we have our PR then from this table, but yet we are not done with this table. Okay, but we'll come back to it. So now we got our PR now to be 0.33, right? This is our PR. So what we can do using this equation, apparently we can calculate our pressure then we solve this question over here. Make the pressure subject of the formula, and then we cross multiply P reduced multiply by P critical. So P reduced, it's going to be 0.33, and then P critical, remember, we found it from the table. So it was, oh. It's very important. By the way, the P critical that I got over there, it was in megapascals, right? So we need to be careful about that. It was in megapascals. So are we using the megapascals? Are we using the megapascals or using kilopascals? We'll use kilopascals, okay? So remember, when we convert megapascals to kilopascals, we multiply by 1,000. So 4.25 multiplied by 1,000 will get 4,250 kilopascals. And then now I'm going to say 0.33 multiplied by 4,250. And then I get 1,402.5 kilopascals. And one of the reasons why do we convert it to kilopascals, because eventually when we substitute our pressure onto this equation, when we want to calculate mass, we're going to need these units which are in kilopascals, right? So now answering this question, we are done. The pressure is this one over here. So to get mass, now is this derived equation that we're going to use. We have the pressure, we have the volume, Do we have the Z? No. Do we have the R? We can get it. Do we have the T? Yes, we do have the temperature. So how are we going to get Z? Now, to get Z, we're going to go back to the table, right? And I want to explain something. I'm going to go back to the table to get Z. So now having a look at this graph over here. On this side, we have this, on this side, we have the saturated line vapor. Then this side, or gas, we have the saturated line liquid, right? So that means what's happening here is that, remember, we said that our T reduced and our P reduced are along this line over here, right? We say they are along this line over here. So this line, it is an isotherm because it connects the points with the same reduced temperature throughout. So it's an isotherm, right? So since well, it is an isotherm, remember along this curve, along this side of saturated gas, at this point over here, just like how we would locate for a specific volume, for enthalpies, and all of those type of parameters here, because we're talking about the compressibility chart. So here we're gonna have the Z. Even this side, we're gonna have the Z. But this Z over here, it's close to saturated liquid, meaning it's gonna be Z of the fluid. And then here, because it is close to the it is on the saturated vapor line, therefore it's gonna be Z of the vapor or gas. So what is the numerical value of this Z over here? By just reading it off from the chart, right? So remember, this is not accurate, okay? It's not going to be 100% accurate. But what is the Z of the gas? So I will say it's 0.8. I'll take it to be 0.85, okay? It's fine. And then here, Z of the fluid along this line, I'll take it as 0.5. Okay. Let me see. Oh, this is 0.1. So I'll take it as 0.05. Right? It makes sense. Let's see. Here we have 0 over here. Yeah, I'll take it as 0.0. Yeah. Set of the fluid as 0.05. Right? If you read it off from there. So make sure you read however you want to read it, but make sure that you come close to the actual value of that you actually need to perform this calculation, okay? Remember, I'm just using this because it's here on the board. I'm not using the rulers, so, but I hope you get the idea. So this is Z of G, this is Z of F. So what I'm gonna do is, not here. I'm gonna go back to the question. Wait, let's confirm our values. Let me write them here down on my book so that I can remember them. Z of G is 0.85. Z of F is gonna be 0.05. So now what are we going to calculate? Let's see. Remember we need Z, right? Not Z of fluid, not Z of vapor. So we're gonna say Z is gonna be equals to, by composition, we're gonna have 1 subtract X, which is the quality, multiplied by Z of the one that we subtract by 1, it's Z of the fluid, plus X multiplied by Z of the vapor. So to determine our Z over here, we have, remember, 1 subtract 0 0.1, and then Z of the fluid, we said it's 0.05, plus our quality is going to be 0.1 again, Z of G is going to be 0.85. And then when we perform our calculations, let me use my calculator. I'm going to say 0.9 multiply by 0.05 plus 0.1 multiply by 0.85. And then I was at this point in time, I get 0.13, which is my C. So now, to further answer our question, we need to calculate mass, right? And again, what is the value of R? It's fine, I'll just plug it there. So to get the mass, I'm gonna say mass is equals to the pressure. We have 1402.5 kilopascals, right? Make sure that you substitute with the units so that you don't make mistakes, right? And therefore, we need the value of, let me see that. Oh, okay, it's fine. I thought I'm making a mistake. And then the V, the volume is 0. Where is our volume? Here we have 0.1 cubic meters. Okay. Divide by our Z, which is got 0.13. Right? And then now what will be the value of R? So the value of R, we're gonna say, remember, the value of R is 8.314, right? So I'm gonna say this value of R divide by the molar mass, right? Remember, I have already got the molar mass from the table of criticals. So the molecular weight, however you want to say it. So the molecular weight was, where is it? Where did I write it? You can also calculate, it's just propane, 3 carbons and 8, I think, hydrogens. But either way, we got it from there. It's 44.094, right? So we're going to substitute this thing over here. So up. So here we're going to have 8.314 divide by 44,094. Then close the bracket. And then our temperature in Kelvin, make sure it's in Kelvin. It's going to be 288. We have 288. So now let me punch in everything on my calculator then. So I'm going to say 1402.5 multiplied by 0.1 divide by 0.13 multiply by fraction 8,314 divide by 44,094, close the bracket, 288. And then let me see. Oh, I said 28,288. And then my answer here, our mass in kilograms. I'm saying kilograms because the value of R here, I used what's this? Like I said, I used the kilomoles. I used for the value of R, I used kilojoules per kilomoles per Kelvin. Okay. And then for M, I used kilograms per kilomoles. Okay. So yeah, so that's why my mass is gonna be in kilograms. So just lazy to write the units because I see again there's no even enough space there, but you can do that. Please confirm the units. 19.87 kilograms, and therefore this will be the mass.